Welcome back, ladies and gentlemen. In this video, we are going to discuss how to go from a complex number form to a polar form of that number. Before we get there, I kind of want to just touch base on something that I hope you've been realizing if you're watching any of the previous videos. There's so many connections between our complex numbers, your typical XY Cartesian plane, what we know about our trig functions and their unit circle, and then the reference triangles and all these things. There's so many connections. They're ultimately in the same, honestly, they're also in the same stuff. It just depends on what mathematical context that we're actually referring to them in. And so what I have on the screen now is just a very basic, I plotted the point A plus BI, okay? That's what you see here in this red dot. That's A plus BI. On the real axis and imaginary axis, we have plotted an imaginary number or a complex number. If you will go ahead and kind of, if this looks kind of wonky to you, you're not really sure where this came from, please watch the previous video on how to plot points on a complex plane. But what I want to kind of show here first and foremost is just the relationship, right, between a typical complex number and the XY axis and the polar axis, which is really just our trig functions, right? So you guys would all agree that the distance, right, from here to here is a distance of A. And really, in the XY axis, that's what X is. And then when you think about it in polar form, well, what is X? Well, X has that relationship with cosine. And if you remember, we solved the fact that cosine theta is X over R. X just equals R times the cosine of theta. So really, that equals R times cosine theta. Well, again, likewise, you'd agree here that this is a distance of B, whatever that coefficient was. Well, what is B? B is the y in the Cartesian plane, and in the polar plane, it's r times the sine of theta. Similarly, the reason why is because if you take the ratio, you get y equals r times the sine of theta there. And again, r, just for the context of complex numbers, we've called it a lot of different things. In the complex plane, we're talking about r is what we call the modulus. The modulus is just simply the distance away from that origin. And so ultimately, that's what we're going to be referring to it as. You've also kind of heard it as absolute value. You've heard it as the hypotenuse of the reference triangle. It's the radius of a unit circle, of the radius of any kind of circle with center of the origin. So there's a lot of different things, but I'm going to refer to it as a modulus because that's where we are in this particular subject. Okay, well, why is this beneficial to us in the long run? Well, if I give a notation of z to my complex number a plus bi, ultimately what we can say now is that if I want to convert from a complex number, which is what we see right here, to a polar form of the number, I can take what I now know about a and b and replace it. And all I have to simply go ahead and do is say that a really is r times the cosine of theta. Polar. R's and thetas are polar. And then b, which is y, times the sine of theta. And I'm going to put the I up front just so we don't get confused of where the I should be. And so what you will really see, I put y instead of r. Let me back up just a bit. So that should be I times r sine of theta. So what we see here is that there is an r in both of these terms. So you will usually see in most textbooks, they factor out that r. And we end up getting here the polar form of a complex number, r times the quantity of cosine theta plus I sine theta. And this is going to help us out as we continue to move on in our kind of context in between our polar forms and complex numbers. So let's take a look at how we can rewrite this with some actual values to them. So first and foremost, we have 1 minus the square root of 3i, and our goal is to put that into polar form. Well, what I like to do first and foremost is just to kind of figure out where are we on the imaginary and real axis or XY axis. Really, I want to know what quadrant we are in. So here we are going to be in quadrant 4. And I know I'm going to be in quadrant 4 because I have a positive 1. I have a negative square root of 3. And then that means I can find that modulus. So r is going to be the square root of 1 squared plus negative square root of 3 squared, which will be the square root of 4, which will be 2. And so that means I will have a value of 2 there. So now at this point, again, remember, I have z 1 minus square root of 3i, and my job is to put that into the form of r times cosine of theta minus I times sine of theta. So let's go ahead and find out what theta is. So what do we know about it being quadrant 4? Well, I know that cosine of theta in this case is going to be the x over the r. I know sine of theta is going to be the y over the r, and tangent of theta is going to be the y over the x. Now, you don't have to write all 3 of those out. I'm just kind of putting this into context with you guys. So this is a nice one, obviously, because this is a ordered pair that is on our unit circle, and it's easy to find that reference angle in theta on the unit circle like this. But the reason why I write all of them out is because, let's say, for instance, it's not so easy, it's not so cut and dry. When you're using your calculator to do your cosine, sine, or tangent inverses, you can't forget about those restricted domains. So if you're in quadrant 4, you're going to probably want to use sine or tangent to find out what that value is, just so that you can go ahead and keep the restricted domain from negative pi halves to pi halves, which it is in both sine and tangent. If you are in quadrant 1 or in quadrant 2, you're going to probably want to use that cosine inverse because it's got a restricted domain from 0 to pi. And then if you are in quadrant 3, it doesn't really matter which one you end up using. I would say universally most people use tangent, just because then you can just add pi or 180 degrees to it. And then it just depends on what, from there, because tangent is going to put you in quadrant 1, and then you're going to add, your pi or your 180 from that. But anyways, let's go ahead and find out what theta is here. So the question is, where in quadrant 4 is cosine 1/2 and sine negative 3, square root of 3 over 2? Well, that is going to happen at theta equaling 5 pi thirds. Now, if you did that on the graphing calculator, it may give, with sine or tangent, it may give you negative pi over 3, which is fine, but usually we try to keep things as clean and nice as possible. So what does that tell us? It means that we have r, which is 2, and we have theta now as 5 pi thirds. And so I'm going to go ahead and actually just leave it just like this. And this would be our finished polar form here. We don't want to take it down any farther, because if we do cosine of 5 pi thirds and sine of 5 pi thirds, it's going to bring us right back into non-polar form. And so you want to keep it in polar form. So at maximum, you'll see maybe that they distribute that 2 to both of those terms there, but you can leave it just like this and it should be good to go. So let's go ahead and try one more. I want to go ahead and take a look at part B that is on here as well. So on part B, let's go ahead and think about negative 3 and negative 4i. So again, I want to go ahead and just draw where we are. It just kind of helps us figure out what life is looking like. So here is a prime example of where I will be in quadrant 3, negative 3, negative 4. It's a Pythagorean triple, so I know for sure the modulus, or r, is going to be 5. If you don't trust me, go ahead. You can go ahead and do your Pythagorean theorem and do it that way, or find the modulus, same thing. But let's take a look at what else do we know. So at this point, negative 3, negative 4, 5, none of these have a spot on the unit circle, so it's going to be kind of an ugly number that we're doing there. So when it's in tangent 3, as I mentioned before, not that you have to, all right, but I would say most people like to use tangent in this case, because when you do the y over the x, you just cancel out the negatives, and so it ends up being positive. And so when you do theta equals tangent inverse of 4 thirds, you're of course going to get it when it's the positive 4, 3 in quadrant 1. So that just means to go from quadrant 1 to quadrant 3, you're going to add pi radians or 180 degrees to the value that you get. So when you actually substitute that into your calculator, for radians, if you're in radian mode, theta comes out to be about 0.927. But again, this is not the angle. This is the angle in quadrant 1. So we want to go ahead and add pi radians to that. So that comes out to be about 4.07. And so now we can say that z is equal to 5 times the cosine of 4.07 plus I times the sine of 4.07. And this is, of course, going to be in radians that they're referring to here. Usually, if it doesn't give you anything specific, these kind of problems are usually in radian mode.